Geothermal webinar series. This is a partnership between ThinkGeoEnergy and Enerchange. And once again, I am Carlo Cariaga, Editor-in-Chief of ThinkGeoEnergy. And today I have the pleasure of introducing a group of very well-respected, experienced, seasoned professionals in geothermal. And we'll be talking about something that is equally important, the Cerro Prieto Geothermal Complex in Mexico, which I think is, in my opinion, is one of the most important geothermal fields. It's certainly one of the oldest, one of the largest, and through the decades of its operations, it has provided the industry with a lot of these lessons, a lot of observations on how reservoir management has to be done. And so our first speaker today will be Luis Carlos Gutiérrez-Negrín. He's a retired Mexican geologist who used to be part of the Geothermal Electric Division of the Comisión Federal de Electricidad. He is currently an independent consultant and executive director of the company GeoConsul. He is also secretary of the Mexican Innovation Center for Geothermal Energy and also editor-in-chief of the Geothermal Energy Journal. He served as president of the Mexican Geothermal Association and was also a member of the boards for the former Geothermal Resources Council and the International Geothermal Association. Our second speaker is going to be Ron DiPippo, who is Chancellor Professor Emeritus of Mechanical Engineering at the University of Massachusetts Dartmouth. He has nearly 50 years of experience in geothermal power and has participated in the development of 22 geothermal fields around the world. Ron has written over 120 technical articles and contributed to and/or edited 9 handbooks dealing with geothermal power. And we wrap things up with Andrew Chiasson, who is a faculty member in the Department of Mechanical and Aerospace Engineering in the University of Dayton in Ohio, where he teaches courses and conducts research in the areas of thermofluid sciences and renewable and clean energy. He has an academic and professional engineering experience in a wide range of geothermal applications. These is related to small-scale electrical power generation, direct use heating, borehole energy storage, and geothermal heat pumps. And so that was a lot, but then I had to rush through them because we're never going to end. So for everyone listening and for the audience, feel free to type in your questions. There should be a questions tab somewhere in the side panel, and we'll get to those questions after the presentation. And now I turn you over to Luis. Luis, please get us started.
Thank you very much, Carlo. Welcome everyone to this webinar. I would like to thank Carlo for the introduction and for the invitation to talk about Cerro Prieto, that, as Carlos said, is the largest and oldest geothermal field in operation in Mexico. The 3 presenters here are also the authors of the book that Carlo mentioned, which is here. Carlo, can you move to the next slide, please? Okay, here you have the book Geothermal Power Generation, which of course was written by the 3 presenters of this session, and the main features of the book you can see in this part. The book has almost 1,000 pages, 28 chapters written by 40 authors from several countries. And we would like here to acknowledge the technical support of the publisher Elsevier and Woodhead Publishing, and particularly the support of our acquisitions editor, Frank Ellis, who had the idea of preparing a new edition of the original book that was edited by Ron DiPippo in 2016. Our presentation here is based on one of the chapters of the book, chapter 27, who was written by my co-author, Ever Diaz-Leon, and myself. Please, the next slide, Carlo. In this next slide, you can see the outline of the webinar. We have divided the webinar in these 3 parts that you can see Here, each one presented by each of the authors of the book and presenters of this seminar. And on the right side, you can see some highlights of geothermal in Mexico in general, and particularly in Cerro Prieto, including the fact that geothermal uses in Mexico started since the pre-colonial times, and that the electric power generation in Cerro Prieto started in 1973, which is more than 50 years ago. Please, next, Gerardo. Okay, let's start with my section. Next, please. Here is the location of the geothermal fields in operation in Mexico, and one geothermal field in standby, which is the yellow triangle that you can see there. And two of these fields are located in the Baja California Peninsula, and the rest in the central part of the country inside the Mexican volcanic belt, which is one of the main physiographic provinces in Mexico. The red triangles indicate the geothermal fields operated by the governmental utility CFE, or Federal Commission for Electricity, and the only red star in the middle of Mexico is the only geothermal field operated by a private company. It is the Domo San Pedro. In the table, you can see the operational or running capacity and the installed capacity of each of the fields, which totals around 1,000 megawatts. Next, please. In this slide, I am presenting the tectonic framework of the region where the field is located. On the left, you can see the North American continent, and on the right, the two main tectonic plates in this area. You can see the Pacific plate on the left and the North American plate on the right, divided or limited by the San Andreas fault system. Cerro Prieto is located in this portion, okay, inside a transtensional basin or pull-apart basin formed by two strike-slip faults called Imperial and Cerro Prieto, which of course are part of the San Andreas fault system. Next, please. Here, in the next slide, I am presenting the tectonic stratigraphic framework of the field. You can see here and here the two strike-slip faults that I mentioned before, Imperial fault on the right here, and Cerro Prieto fault here. In this region, the Pacific plate is composed in its basement by the Baja California terrain, tectonic stratigraphic terrain, which in turn is composed of granitic rocks of Cretaceous age. On the right, the North American plate in this part is composed of the North American stratigraphic tectonic stratigraphic terrain, which in turn is composed of metamorphic rocks of Paleozoic to Mesozoic age. In the central part, you can see the pull-apart basin, the transtensional basin, in which are the pre-oceanic rocks, which is composed of pre-oceanic rocks. You can see also some tertiary, maybe Pliocenic basic intrusives, I mean of basaltic or gabbro composition, in which the field is located. I would like also to mention the dashed red line here from southwest to northeast, along which the technical personnel of the CFE prepared the conceptual model of the field, that we can see in the next slide. Please, Carlo. Okay, here you have the conceptual model of the field. On the left, you have southwest, on the right, northeast. On the right is the vertical scale from 0 to 7 kilometers, and you can see here also the two faults that I mentioned before, the Cerro Prieto fault and the Imperial fault on this part. These are strike slip faults, but also have a very important vertical component, as you can see, normal component, as you can see here. The red lines, vertical lines, are production, injection, or exploration wells drilled in Cerro Prieto and grouped in the four sections in which the field is divided for administrative reasons, called Cerro Prieto 1, CP1, Cerro Prieto 2, CP2, CP3, and CP4. You can see also that the subsurface is divided, has been divided in these three main lithological packages. The first of which is this yellow package, which is called, composed of unconsolidated clastic sediments, and I mean sediments like gravel, sand, silts, and so on of quaternary age. Below or behind of these packages is a package of tertiary to quaternary age composed of shales. Main amount of the shales are these called gray shales, and a small package of brown shale. The shales are intercalated with several lenses of grauwackas, gray wackas, or sandstones, where the geothermal fields, the geothermal fluids are contained. And in the third lithological package is the basement, composed of the three sections that I mentioned before: granitic rocks here, metamorphic rocks here, and some tertiary intrusives, one of them being the heat source of the geothermal system. The thick horizontal red line indicates the isotherm of 300 Celsius, 300 degrees, and the thick green line indicates the first appearance of epidote, which is replacing the matrix of the sandstones and is a very important marker, hydrothermal marker in the field. Next, please. Okay, here are some interesting reservoir, interesting features of the reservoir at the subsurface, including this area where some condensed steam started to be formed since 10 years ago. This is the situation for 2015. I would like, you can see also here the location of the power plants CP1, CP2, CP3, and CP4. And these lines, black lines, indicates the limit of another structural system, in this case transversal to the main structures of Imperial and Cerro Prieto, and composed of faults and fractures, which is very important for the permeability in the subsurface. It is called by the technical personnel of CFE the age fault system. And in the table that you can see here, there are some average composition of enthalpy, temperature in Celsius degrees, wellhead pressure, and total dissolved solids in each of the sections of the field, CP1, CP2, CP3, and CP4. Next, please. Here I am presenting the injection system in Cerro Prieto. On the right here, you can see a very simplified schematic with some production wells grouped or isolated, as you can see here. And here are the separators in which the geothermal fluids are separated in the two phases, the steam phase and the liquid phase. The steam, of course, is collected and sent to the turbines, to the power plants, through the net of pipes, and the brine, the liquid phase is also collected, and a small part of this brine is injected in some isolated injection wells, but the bulk of brine is sent to these evaporation ponds through open channels, which was built in 1984 over an area that you can see here of 14 square kilometers. The brine reaches this point, which is where are a couple of pumping holes, and since there, it is pumped inside the evaporation pond in this spiral trajectory up to reach this point, which is the main pumping hole, from where it is sent to the injection wells that are marked here in red circles. During this trajectory, the brine reduces its temperature, of course, and deposits some minerals that, in its composition, particularly silica, SiO2, and eventually is returned to the reservoir. Of course, approximately half of the brine is evaporated along this trajectory due to the high ambient temperatures in the field that can reach 40 Celsius degrees in summer, and the other half is effectively injected into the reservoir. Next, please. Okay, I would like to finish my part just presenting some, let's say, historical milestone in Cerro Prieto. Since 1958, when the first geological survey were made by personnel of CFE, up to 1973, when the first two power units started to operate in the field. In the graph that you can see on the right is the, let's say, the evolution of the installed capacity in the field. You can see here the megawatts and here the years since 1973 up to now. As you can see here, the top installed capacity in Cerro Prieto was reached in the year 2000 when with 720 megawatts, and then the oldest 4 units were stopped and eventually removed from the field to reach the current installed capacity of 570 megawatts, even though the actual generation is around 300 megawatts. This is all from my side. I would like to pass the floor to Ron DiPippo. Thank you.
Thank you, Luis. And to all of our webinar viewers, welcome and thank you for tuning in. I'm going to be talking about the power plants and service installations. And what Louis just told you was that the first power plant came online in 1973. Now, those of you who are as old as me or perhaps close to my age, remember that 1973 was a very important year in the history of the world. It was the day, the year of the first oil embargo. And that sent oil prices skyrocketing and sent countries looking for indigenous sources of energy. And there it was in Cerro Prieto, starting in 73 with their own geothermal power plant. And while they were developing the field, along comes the second oil shock in 1979. And that was the year that additional power units came on. And that impetus to develop geothermal spread around the world. And even so, at that time, the only real large geothermal plants in the world were in Gutiérrez-Negrín in Italy and in the geysers in California. But liquid-dominated resources are the predominant ones in the world, and Cerro Prieto was the third one to figure out how to develop it. New Zealand was there a little bit earlier, and a small plant in Japan. But at this point, I think we can move. Hopefully, the next slide will show up. Thank you very much. Okay, this is the current situation. We have 4 power plants. I define a plant as a powerhouse. And within those powerhouses, there are 9 operating units. Every unit corresponds to a generator. And as Louis pointed out, total generation capacity is 570 megawatts. And they are distributed between single and double flash type plants, with 100 megawatts in single flash and 470 megawatts in double flash. And to date, there has never been a binary power plant in operation at Cerro Prieto. Next slide. This is an aerial view of the field, and you can recognize the evaporation pond that shows schematically, along with the 4 separate power plants designated as CP1, 2, 3, and 4. As you can see from the scale on the screen, this is a 2-kilometer distance, so the entire field is contained within approximately 10 square kilometers or so, maybe 15. And by the way, I'm going to be using this slide quite a lot, and I'm going to focus in on it. This came from Google Earth, and it was in November of 2022. There were more recent images, but the infrastructure really hasn't changed much, so this was to give you a visual of the entire field. And I think I should point out early on that this field is very, very flat. The terrain has very little relief in it. There's a difference of a few meters across this entire area. Something the whole field in the area is about 35 square kilometers, and it is extremely flat, which makes it pretty easy to move drill rigs around, lay piping for the power plants, etc. Next slide, please. I'm going to start with the obviously the oldest plant, CP1. This was installed in 73 with the first 2 35.5 megawatt units. These things ran for 38 years, and they were turned off in 2011. The next 2 units came on 6 years later, same identical units, single flash, and they would put out of commission in 2012. So there was quite a period of time when both of these were operating and serving the system quite well. In 1981, the unit number 5 came online, giving an additional 30 megawatts, and that unit is still running today, in spite of the fact that the old units are gone. Unit 5 with 30 megawatts continues operating. If I can have the next slide, please. Yeah, we're going to focus in a little bit on this one now. This is CP1, and you can see that there is a powerhouse here. There's the switch yard. There were cooling towers here that served the first 4 units, and they are removed. And at this end, you can see a small cooling tower. That is the one that serves Unit 5, which is in this far end of the building. Next slide, please. This is a photograph of the power plant when it was in full operation, CP1. You can see the very large barometric condensers for each unit. And you can see here a simplified flow diagram for the entire operation. In the case of CP1, these wellhead separators were located at every single wellhead. Every well had one of these and a steam line which went across the field and came to the powerhouse to drive the turbines. The liquid from those separators initially was sent to the evaporation pond. But when 1981 came along and they put in the lower pressure unit, which turns out to be a double flash unit, they were able to use that brine and generate 30 megawatts more without additional wells. This is a smart move, and perhaps this was the first time that this had been tried at a power plant. And it is a standard now way of capturing as much energy as you can from the brine by using bottoming cycles. Fairly standard. This number 5 unit, however, used a low-level condenser, so you don't see one of the barometric condensers outside this unit, because the condenser is beneath the turbine buried. Next slide, please. This is what those condensers look like. They're very tall. They rely on the principle that atmospheric pressure will raise a column of water about 10 meters, and above that column is essentially a vacuum. Over on the left side here, you can see the exhaust from the turbine brought up and discharged into the upper section of the condenser, in which cold water is sprayed through the top. Now, these are the pumps that can pull the cooling water from the cooling tower pits and discharge it here. So you get this mixture. The next slide, go ahead, next slide. The next slide shows the inside of the powerhouse with the generator and the turbine. The unit in front here is the generator, the turbine is behind it. The reason they used that barometric condenser was because at the time, that was the simplest way to condense. No moving parts inside. And it had been used at the geysers, for example, in the early units, and they adopted it here. Once those units were removed, no further barometric condensers are used anywhere in the field, and all the units that we talk about are then using low-level direct contact condensers. Next picture, please. Okay, the unit number 5 required that all of the liquid being separated at all the wells be conveyed through pipes to a central location, a flashing station. And it was done so, as you can see in the schematic, by first sending those that pressurized liquid to a first bank of flashers. These are the medium pressure flashers that produce steam, which was then sent back to the unit, the powerhouse. The liquid from the first phase of separation went down to 2 other additional flashers, 2 for each of those, and produced the low pressure steam and sent that to the powerhouse. The remaining liquid, which is now highly supersaturated in silica, is collected and immediately dumped into the evaporation pond. So this is the picture of the units with the medium pressure separators in the front, and the 6, you can only see a few of them in the back. Next slide, please. Now, getting back to our overview, here's where that station was located. Mind you, this is where the power plant is up here. This was placed right at the edge of the evaporation pond so that that highly supersaturated brine could be discharged quickly into the pond and not foul the pipes. Next. flow diagram, heat balance diagram for unit number 5. I'll just point out a couple of things fairly standard. Notice that at the end of all the separations, there was 650 kilograms per second of brine that went into the pond. That's a lot of fluid. And notice also that the pressure in this separator is about 2 bar, so it's above atmospheric pressure. So that even in those short pipes, but it finally got to the end of the pipe, there was yet another flash process which produced some vapor, and all that liquid then went into the pond. The rest of this is fairly conventional, and I don't think we need to go into any of that. Next slide, please. Yeah, Cerro Prieto 2. This is the first of the modern plants, they call them. There are 2 units of 110 megawatts each in that power station. They started up in 1984 and they're still running today. Next slide. Again, back to our map. Here is number 2, which is in the southern part of the field. It's about 1.5 kilometers from unit 1, which is up in this area of the map. And you can see here's the powerhouse. There were 2 large cooling towers, one each for the 2 units. And by the way, when you see a cooling tower like this and there is no vapor coming out of it, it means that that unit is not in operation. And since these are fairly recent, you can get an idea of how many units are actually operating in 2022. There's a set switchyard is here. And in the case of these units, every well had both a separator and a flash vessel right at the wellhead, so that you had 2 separate pipelines carrying the steam to this unit. Next slide, please. And unit 3 is identical to unit 2, so it's not worth spending much time here. They're 2 identical units. Next slide. And you can see that it's up here a little bit away from, it's about 3 kilometers away from unit 2, up in the northern part of the field. And again, you can see the setup, it's identical, except here again, this unit is running and this one is idle. Next slide. This is courtesy of Toshiba, who supplied the units. Again, you can see down at the bottom here, the steam pipes, the high, medium pressure, low pressure. And these are moisture separators that are right outside the powerhouse to remove any liquid that might have condensed in the steam lines coming from across the field. Next. And just a photograph inside the unit. I took this one in 1984. The unit had just come online. This is the generator, 110 megawatts. These are 2 55 megawatt double flow turbines. Here it is on the test stand in Japan. And this is a cross section of the turbine with the high pressure coming into the middle section, and then the low pressure steam mixing with that and going through the rest of the turbine and out. There are moisture removal sections to remove some moisture, which prevents erosion of the turbine. Next. Again, the flow diagram. Remember, this is one of these arrangements is sitting at every production well, both for units 2 and 3. And the turbine is here, tandem compound, low-level condensers. Notice the non-condensable gases, which have to be removed because you get CO2 and H2S, perhaps some other things mixed in with the steam. So you pull them off, and normally you just use a steam jet ejector, but in this case they use turbo compressors. And the turbo compressor, here's the compressor that sucks the gas out and discharges it through a vent. And that compressor is driven by a small steam turbine, which gets its steam from the high pressure header. But after it's used, they don't simply dump it into the condenser, but they return that, it's still under pressure, they return it to the low pressure steam header where it can go through the turbines and generate some more electricity. That's a novel feature and it is an efficiency improvement. Next. And come finally to Unit 4, which came online in 2000, 4 separate units of 25 megawatts. They've been running for 25 years, doing fairly well. Next slide. Okay, that one is the one that's in the far eastern part of the field, very close to the limit of the field. A large powerhouse with 4 identical 25 megawatt units there, each one served by a 3-cell cooling tower. And again, you can see one of them is not operating today. We took the picture here. Google took the picture. And this is served by wells in this part of the field. Next slide, please. Here's the unit, and here is a typical separator station and a smaller one down here. This is where all the steam which is gathered from the wells all around this area are brought and separated, and then the steam is brought over to this power plant through the pipelines, as you can see. The liquid from this and other separators, which are off in the distance behind this, up in the northern section, they're thrown discharged into a canal, an open canal, concrete canal, which runs to the west and goes into the evaporation pump. I've accentuated the color so you can see it, but the next slide shows you the actual color as seen from satellite. And you can notice that it's a bright light blue, which indicates colloidal silica in solution in the brine, and it is saturated and supersaturated. Actually, when it gets to the pond, it immediately starts to precipitate out. There's also another canal, which you can see here, channel, that's collecting liquid from the southern part of the field, brings it over, and they merge at this point and go down to a single place where it goes into the pond. Next slide, please. A picture of one of those separators. Again, you can see how flat the terrain is, just like before in your house. And here we have the aerial view of all the units with all the pipe. There is a lot of pipe, about 140 kilometers of steam and brine lines in the field. As I said, fortunately, it's flat and fairly easy to set that up. Next slide. Okay, we can pass from this. This is just a standard schematic. Next slide, please. Okay, this is a summary for those of you who are interested in some of the technical specs on these units and who supplied the equipment for the turbine. I will only point out the efficiency values here in green, and if we come over to the newer plants, you can see that the turbines operate with an efficiency of about 80%, 82 for the high pressure, 79 for the low, and 78, 79 for the smaller units. The specific steam consumption tells us how many kilograms of steam we need per megawatt. Here you can see it's about 2 kilograms of steam per second will give you a megawatt. Utilization efficiency is important, and you can see for the double flash units, it's about 48%, and for the single flash units, about 40%. This is very good. These numbers can be compared to the efficiencies that you may know for nuclear plants, which is 33%, and for coal-fired plants, which might be 35, 37, 38%. And certainly the highest efficiency of combined cycle gas turbines, steam turbines, they're about 50%. So geothermal plants are not inefficient, as some people thought. They're actually quite efficient and certainly hold their own against conventional plants. Next slide, please. This is the installed capacity. Louis already showed this, so next slide, please. Okay, this is the important output of the plant. This is the electricity that is generated. It's important because this is the product that is sold. This is where the revenue comes to pay for all the well drilling, the piping, the turbines, maintaining the operation of the plant. And as you can see, it reached the peak of 5,500 gigawatt hours in 2005. This when everything was running and going really smoothly. But then you'll notice that this is not a good trend, as the generation is falling off quite rapidly. And another way to look at that in the next slide is to look at the capacity factor. This tells you the percentage of the maximum possible generation, which if every unit ran at its installed value for an entire year without any stoppage, then you would generate the maximum electricity. This one tells you that, well, we did 91% of that. That's pretty good in 1978. But then there have been fluctuations. And again, after that peak year, when it was about an 87.5% capacity factor, which is a very good number, it started to drop off. And now it's less than 50%, which is what you saw in those pictures, that half of the units are sitting idle, basically. And that is not good. It tells you that the field has matured. It may be overdeveloped at this point. And what normally happens under these conditions is that you reassess the reinjection program and try to find a better way to reinject the fluid so that you can maintain pressure and extend the life of the field. Now I think I'm done. The next slide shows Andrew's face, then we're going to listen to him. Andrew will take us the rest of the way. Thank you very much.
Thank you, Ron. Thank you, Louis and Carlo and everyone else in attendance. The third and final section of our presentation is lessons learned and the future insights from what we learned about these lessons. So much of what we've learned from Cerro Prieto Complex has really made its way into what we think of now as general or standard of practice for new fields being developed. And this is the first one that we hear quite a lot, especially those of you who are new to geothermal, is that it provides sustainable baseload power. And Cerro Prieto has demonstrated that with over 50 years of operation. And as both Ron and Louis pointed out, some of the years have seen over 80% annual capacity factors, meaning essentially they work about 80% of the time over the year. And since that time, that's offset about 5 million barrels of crude oil on an annual basis. The other big lesson that's been learned is the brine management scheme, which we now put into geothermal practice, is something that started from the very beginning of the reservoir concept and development. And that is because, as we know, we have to replace the brine for mass balance and pressure sustainability reasons of the reservoir. But it's not as easy, as you can see in the second bullet, it's not as easily done as said, because Cerro Prieto learned that because of the high salinity brines, that injection is not so easy, hence the blue lagoon that Ron pointed out with no tourists. The other thing that we now can take as standard practice is reservoir modeling and simulation. And back in the 70s, that was quite a bit different from today with computer simulation and AI and things like that. But as Louis also pointed out, the concept of the reservoir at Cerro Prieto was still somewhat developing. But knowledge of where you're going with the simulation and the reservoir modeling is a valuable tool to managing it. And with the reservoir management, Cerro Prieto taught us some things about managing the resource as a whole and being able to diversify beyond just electricity generation dramatically improves the economic viability of some of these fields. And one of those ideas was brine mineral recovery. As was pointed out, there was silica bricks and other things that were tried at Cerro Prieto. They may look good and they are good on paper, but translating that into a field situation does have technological and economic barriers and challenges with field scaling, as well as the business modeling of the undertaking. And as Ron pointed out, Cerro Prieto actually taught us a lot of innovative things about steam management and steam process optimization, being double flashing, optimizing the separator pressures, and Ron discussed the introduction of the turbo compressors for the non-condensable gases, Lots of creativity and things like that came out of this Cerro Prieto cycles. And eventually there's talk of going to binary bottoming cycles. Okay, the next slide here is the lessons learned. And if you notice, the inner circle here is some of the things from the previous slide. So outcoming from the brine management scheme and some of the other things that are next to it are the so-called advanced geothermal systems. And so those, as you know, do not rely necessarily on the presence of underground fluids, the closed technologies. And so it eliminates all of the issues of brine management and handling of them. And the other thing that it simplifies is the reservoir concepts. As you know, we're not drilling and looking for hydrothermal fluids, we're looking for heat. And so that simplifies the concept as well as the target. And so with that it does change, and even without that, we now have quite a bit more computing power and tools to do 3D and other enhanced reservoir simulation and visualizations with animation and AI and so forth. And as we know, still, and talk about a lot in geothermal circles, is if we could improve the economics with cascaded uses, that really increases the bottom line. And some of the obvious things and talked about things are district heating and cooling in warmer climates, advanced geothermal refrigeration with heat-driven heat pumps, absorption, adsorption cycles. Mineral recovery, as we know, we hear a lot about that with lithium recovery and other valuable minerals that are laden in the geothermal brines. And with that, though, it's all for naught if we don't have a good business development model or business model and somebody to actually run the undertaking effectively. The other thing that came out of Cerro Prieto too is the regulatory and community framework. If there's policies in place and other frameworks in place for workforce development, that it dramatically enhances the acceptance and development of a geothermal project. Okay, well, finally, thank you for staying with us for all this time. So just to summarize the highlights of the presentation is that the Cerro Prieto complex has really been one of the bright spots of geothermal. It's been going for 50 plus years and still successfully generating geothermal electricity. As Lewis pointed out at the beginning, it's a very large liquid dominated field. It's over 15 square kilometers and quite high average temperatures and pressures over normally 300 C and above, and 140 to 180 bars, where a bar is about an atmosphere, so over 200 atmospheres of pressure. Geologically, the field lies in a pull-apart basin, which is an extension of the San Andreas fault system that extends into Baja California, Mexico there. And as all of us said, the brines are very highly saline and very rich in dissolved solids, and hence that presents a challenge on injecting the brines, but results in a beautiful blue lagoon. And now we have 4 power plants with 9 individual power units. And as both Ron and Luis mentioned, as the plant or the complex peaked at 720 megawatts in the early 2000s, and now is down to 570, which is for Baja California homes, that's almost all of the residential load in that area, about over 1.3 million homes or so. And like I was saying, the field, although we may not have think of it because it now seems in somewhat common practice, it taught us lots of things originally back about brine management, injection strategies, control of mineral scaling, and how to reservoir or sustainability manage the reservoir. So the final summary then is just how the field developed in a conservative way with some small units, and then it started to expand and went and as the newer areas of the complex became discovered and utilized, and then now finally the field has reverted back to 4 small units once the limits of the field had been discovered. Okay, so just a couple more slides before we conclude and take questions. A couple of references for further reading are chapter 27 in the book that Lewis had highlighted on slide 3 there, which is the second edition of Ron's first edition of the Geothermal Power Generation Developments and Innovation, and in the second edition, the editors are the three of us speakers. And then there's some other, an earlier work in Ron DiPippo's third edition of Geothermal Power Plants, Principles, Applications, Case Studies, and Environmental Impact, and that's chapter 13 in that book on Cerro Prieto. And lastly, we'll end off with some inspiring words by Luis Francisco Nandana, who is considered Mexico's father of geothermal energy, on the occasion here of his Pioneer Award, GRC. But back to lessons learned, for Cerro Prieto and Mexican geothermal to be so successful, these projects are really beneficial with a champion such as Luis Francisco here. If some development or country nationally can be championed with unwavering support and career dedication with a fellow such as Luis Francisco, it dramatic benefits in the development of the geothermal power sector, as we've seen in Mexico. Again, thank you all for your attention, and on behalf of Luis and Ron, we thank all of you, and we're willing to answer any questions as best as we can in the short remaining time that we have. Carlo, to return it to you.
Okay, then. Thank you, Luis, Ron, Andrew, for that, for telling us all about the story of Cerro Prieto. I definitely believe it's one of the most important projects for geothermal energy in the world. But then it was also a learning process, I believe, and this is also the same case for a lot of the older geothermal fields, for the geysers, for Wairaki, especially in the field of reinjection and brine management. So. My question is, can you give some insights? I suppose since then a lot of modeling has been done in Cerro Prieto, and what would have been a more sustainable reinjection strategy if we had the knowledge that we had right
Oh, Luis.
Yeah. Can you repeat? I didn't hear very well your question, Carlos, please.
now? Okay, sorry, Luis. If we had all of the knowledge that we had right now, what would have been a more sustainable reinjection strategy in Cerro Prieto, such that it would have been able to sustain at its full installed capacity?
Yeah, I think that is one of the main conclusions of the way in which Cerro Prieto was originally managed, because injection in Cerro Prieto started several years before, after the production start in the field. And even now, only more or less half of the brine is reinjected to the reservoir, because of the use of this evaporation pond. So one of the main conclusions that was remarked by Andrew is that we need to start the injection since the very beginning of the production of any kind of any field. And if the field has not enough brine to be reinjected, as is the case, for instance, of the geysers, try to use water from some place else and inject. Of course, in the case of Cerro Prieto, this the situation. I mean, in 1973, there were still many concerns that the injection in one field, in one geothermal field, could cool the results at the subsurface and so on. So that was that of course we know now that injecting in the correct places do not imply any problem. But to me, and it's one of the conclusions that we wrote in the chapter, that is one of the main conclusions. We need to start injection since the beginning of exploitation of the field. I don't know if Ron, Andrew.
Yeah, I was going to say the same thing. Thank you, Luis. That basically the field kind of got behind by not injecting at the beginning. The mass balance was already in favor of not replenishing the water. But in injection 101, if I might call it, typically we say maybe even twice as many injection wells sometimes help relative to the production well. We need more well length and where exactly to put the injected water where it's permeable enough for the reservoir to accept it. So reservoir modeling helps those questions. But also, again, since they didn't start from the beginning, they were already behind in sort of where the water would be going and catching up with the drilling of extra injection wells. Then you run into extra costs that may or may not have been planned. But something is modeled and understood from the beginning. So now when we drill, we also drill and test injection wells and make sure it can handle like double the capacity or something like that of the flow rate.
If I may, this is not meant as a criticism of the way the field was developed. If you remember back in 1973, the only large liquid-dominated field was in Wairaki in New Zealand, and they didn't re-inject either. They simply discharged the fluid into the Waikato River. So people were afraid to do the re-injection back really because they didn't understand what would happen. So it's not a criticism of it. And given the high concentration of solids, it was a challenge, would be a challenge actually to try to re-inject that fluid without removing the solid first. And that's what the evaporation pond is meant to do. It's meant to set out get the silica out of the solution and then re-inject relatively clean brine.
Yeah, I guess it is worth mentioning that this is not criticizing how Cerro Prieto was developed, because at that time, there was not a standard injection strategy for any geothermal field in the world. And so it was a process of learning by doing, I suppose, for the whole industry. Okay, then we have a few more questions from the audience. Let's go into them a bit more. A few questions about chemical treatment. Is there also some sort of upstream or downstream anti-scaling treatment using chemicals in Cerro Prieto?
I do not know that. This is Ron. Perhaps Luis is closer to that field and maybe he understands it, but I have not seen any anti-scaling treatments reported in the literature. There may be some going on that's not reported. I'm not sure.
This is Andrew. I'm also not aware of any unless there's some mechanical filtering. To my knowledge, there's no other chemical treatment. Do you know, Luis?
Yes. There has been in the past some demonstrative projects and to try to use downstream the brine, particularly the brine, for several direct applications. No? The CFE, the CFE conducted some experiments and some demonstration projects to use the silica to build bricks and something like that. No? Use the brine for develop some hydroponic developments and so on. No? And of course, the original idea of the evaporation pond was to use the solids in the brine to collect basically some chlorides of potassium and calcium, if I don't remember, but to produce fertilizers. this project was started by a company which is not existing now. But in this moment, I think that there are a lot of possibilities and projects that the CFE can do, maybe associated with some another parts of the government or private investment and so on. But the main problem now is try to get a better production of electricity in the field.
Okay, then we have a couple more questions related to chemistry. Has there been significant corrosion on the wellheads or other surface facilities in Cerro Prieto? And also the second question is that have there been any other critical mineral or critical metals that have been identified in the brine of Cerro Prieto? Like, for instance, what is the lithium concentration for the brine?
Well, corrosion problems, there have not been corrosion problems in Cerro Prieto. The only problems of this in this regard are in some wells in the most easternmost part of the field, where some very deep wells produced some acidic fluids and so on. But in general, there has been not a problem in the field. Sorry, the other part of the question.
Oh, sorry. It was about the concentration of other critical metals or critical minerals. So, is there a high lithium concentration in the brine in Cerro Prieto?
Yeah. One of the future projects of CFE could be try to again exploit the lithium in the brine. No? I mean, it is in Cerro Prieto the amount of lithium is around 1/10 of the amount of lithium in the fields of the Salton Sea, for instance. I mean, it's not a lot, but it is enough to try to be recovered, considering the high prices and so on that the lithium could have in the future. In this moment, they have no very high prices, but I think that it is one possibility in the future for CFE because the main investment has been done in the evaporation pond.
How about efforts for recovering silica in the past? Has there been any challenges, say, in making it cost effective or commercial?
Well, as I mentioned before, in the past there were some projects to try to do that. No? In those times, there was no commercial market for the silica. No? So the main deposit in the evaporation ponds is the silica, and CFE has to drag the pond every year, sometimes twice a year, to remove all the silica deposits. But as far as I know, all this silica is just disposed in another places, in safe places, of course. It's not a very reactive component, but it could be maybe now if we have some CFE or in the region, there are some possibilities to use the silica in some applications. Could be again a good possibility.
Okay, here's another interesting question. In the past, when there was not yet reinjection in Cerro Prieto, has this manifested, say, in say subsidence or earthquakes? Have there been more geologic effects of the lack of reinjection?
Well, yes, there has been some studies about the subsidence in the field along the years, um, and new for due to the extraction of the fields, of course, and the low rate of injection in the same place. As far as I know, there has been no any big problem with this rate of subsidence in the field, but I am not familiar with the process.
Okay, then we are a little about over the time now, so maybe let's wrap up with just one more question, just one last question to finish things up. This is open for everyone, but what do you think is, say, the most important lesson on reservoir management that we got from Cerro Prieto that you think has been applied to other geothermal fields in the world?
I would say, in my opinion, reservoir modeling and simulation. Now, with our knowledge from fields like Cerro Prieto, we know what to look for, and then with predictive modeling and based on a set of field data, we can get a lot better idea of where fluids are coming from, and especially where they're going to when they get put back in the ground.
Yeah, I dare say that the Cerro Prieto field has really been studied from a reservoir perspective. I mean, you have the IIE doing the science, you have CFE doing the production, you have Lawrence Berkeley Lab running their models on it. An immense amount of study has been directed to Cerro Prieto, and the lessons learned from that really apply to any liquid-dominated field that you have in the world. So it's been studied and disseminated. That information is out there, and I'm sure that people appreciate that when they go to develop a new field.
Luis, would you like to add anything before we wrap things up?
Well, no, I agree with Ron and with Andrew. Cerro Prieto is one of the geothermal fields in the world better studied and known. I mean, on the general characteristics, but I don't have much more to comment.
Okay then, and I think that's a lot for today's webinar. Thank you to the three of you, Luis, Ron, and Andrew. That was we learned a lot about Cerro Prieto and definitely about standard reservoir management for geothermal fields now that we know what works and what doesn't. So thank you to all the speakers. Thank you to everyone who attended, and we shall see you again for another webinar in 2 weeks. Have a happy weekend.
Thank you.
Thank you very much.